Well, I've got a lot planned for this hour. Basically, I want to tell you a story that's been unfolding for me for about the past 40 years, and that's just coming to fruition in a really exciting way. And by just coming to fruition, I mean pretty much today, because I'm planning to show you today a whole lot of technology that's the result of that 40-year story, and that I've actually never shown before. I think is going to be pretty important. I always like to do live demos, but today I'm going to be fairly extreme, showing you a lot of stuff that's very, very fresh, and I hope at least a decent fraction of it is going to work. We shall see. Okay, so here's the big theme: taking computation seriously, really understanding the idea of computation, and then building technology that lets one inject it everywhere, and then seeing what this means. So I've pretty much been chasing this idea for 40 years. I've been kind of alternating between science and technology in doing that, making these sort of bigger and bigger building blocks, kind of making this taller and taller stack. And every few years, I've been able to see a bit further, and I think made some interesting things. But in the last couple of years, something really exciting has happened, some kind of grand unification, which is leading to sort of a Cambrian explosion in technology that we can build, which is what I'm going to be showing you pieces of here for the first time today. Well, okay, for context, let me tell you a bit of the backstory. About 40 years ago now, depressingly long time, I was a 14-year-old kid who just started using a computer, which in those days was about the size of a desk. And I was using it not so much for its own sake, but instead to try and figure out things about physics, which was what I happened to be really interested in. And I actually figured out a few things which still even get used today. But in retrospect, I think the most important thing I figured out was kind of a meta thing, that the better the tools one uses, the further one can get. Like, I was never good at doing math by hand, which in those days was a problem if you wanted to be a physicist. But I realized that one could do math by computer. And I started building tools for that, and pretty soon, me with my tools were better than almost anyone else at doing math for physics. And back in 1981, somewhat shockingly in those days for a 21-year-old professor type, I turned what I'd done there into my first product and my first company. And one important thing is that made me realize that products can really drive serious intellectual thinking. I needed to figure out how to make a language for doing math by computer, and I ended up figuring out these sort of fundamental things about computation to be able to do that. Well, after that, I dived back into basic science again using my computer tools, and I ended up deciding that while math was fine, the whole idea of it really needed to be generalized. And I started looking at sort of the whole universe of possible formal systems, in effect, sort of the whole computational universe of possible programs. And I started doing little experiments, kind of pointing my computational telescope into this computational universe and seeing what was out there. And it was actually pretty amazing. Let's see, here should be a few little programs that one can see out in the computational universe. And some of them do very simple things, but some of them, well, they're not simple at all. Let me show you my all-time favorite. Because it's the first one I ever saw that did anything like this. It's called Rule 30. I still have it on the back of my business card 30 years later. But it's a trivial program, trivial start, but this does something pretty crazy. It sort of just makes complexity from nothing, which is a pretty interesting phenomenon that I think, by the way, captures a big part of sort of the secret of how things work in nature. And yes, I've spent years studying this, and it's really interesting. But when I first was studying it, the big thing that I realized was I need better tools. So basically, that's why I started out building Mathematica. It's sort of ironic that Mathematica has math in its name, because in a sense, I built it in order to get beyond math. In Mathematica, my original kind of big idea was to sort of drill down below all the math and so on that one wanted to do and find sort of the computational bedrock that all this stuff could be built on top of. And that's how I, for example, ended up inventing the language that's in Mathematica. And over the years, it's all worked out really well. We've been able to build ever more and more on it. In fact, Mathematica just celebrated its 25th anniversary this year, and in those 25 years, it's gotten used to invent and discover zillions of things, and it's used in pretty much all the universities and big companies and so on around the world. And actually, I myself managed to carve out a decade in the middle of this to actually use Mathematica to do science myself, and I ended up discovering lots of things, scientific, technological, even philosophical, and ended up writing this this big book about all of that. Well, okay. Back when I was a kid, something I was always interested in was systematizing information, systematizing knowledge. And I had this idea that one day one should be able to build something that would automate being able to answer questions about basically anything. And I figured out a lot about how to answer questions about math computations, but somehow I imagined that to do this in generality, one would need sort of some kind of general artificial intelligence, some sort of brain-like AI thing. And that seemed very hard to make. So every decade or so, I kind of revisited this question and concluded that, yes, it was still hard to make. But doing the science that I did, I realized something. I realized that even if one just runs a tiny program, it can end up doing something like this. It can end up making all sorts of great complexity that's actually kind of brain-like complexity. What I realized, and there's a whole lot of kind of science behind this, is that there isn't really ultimately a distinction between kind of brain-like intelligence and just this computation. And that's got lots of implications for things like free will versus determinism and things like the search for extraterrestrial intelligence, all kinds of things. But for me, it also made me realize a very practical thing, that you shouldn't need a brain-like AI to be able to answer those questions about everyday things. Maybe all you need is just computation, and like the kind that we'd spent years building in Mathematica. So I wasn't sure if it was the right decade, even the right century, but I guess this is sort of an advantage of having a simple private company and being in charge, that one can decide to do the experiment anyway. So I'm happy to say that, that it worked out, and we ended up building Wolfram Alpha. So, you know, the idea of Wolfram Alpha is you type stuff in natural language, and Wolfram Alpha will try and use all the curated data and knowledge and methods and algorithms and so on that it has to basically generate a report about what you asked. And yes, if you're a frequent Wolfram Alpha user, you will notice that Wolfram Alpha just yesterday actually got a nice spiffier look on the web. Well, Wolfram Alpha knows about all kinds of things. Thousands of domains of knowledge, trillions of pieces of data, and indeed, every day, millions of people ask it all sorts of things, directly on the web, through its apps, through things like Siri that use it. Okay, so we have all of this knowledge and computation capability in Wolfram Alpha. We also have Mathematica, which has this kind of bedrock language for describing computations and for doing all sorts of technical kinds of computations. With Wolfram Alpha, we have something that knows a lot about the world, and which people interact with this through this sort of much messier natural language kind of interface. Well, Mathematica has been growing for more than 25 years, Wolfram Alpha for nearly 5. We're continually inventing ways to sort of take the basic ideas of these systems further and further. But now something really big and amazing, as far as I'm concerned, has happened. Actually, for me, it was catalyzed by another thing, which is the cloud. Well, I didn't think the cloud was really an intellectual kind of thing. I thought it was just kind of a utility that was out there and useful. But I think I was wrong, because I finally understood how it's sort of the missing piece that lets one take the two big approaches to computation in Mathematica and Wolfram Alpha and make something just sort of dramatically bigger from them. Now, I've got to tell you that what comes out of all of this is actually pretty intellectually complicated. It's also very, very directly practical. I always like these situations where sort of big ideas let one actually make really useful new products. And that's what's happened here. We've taken sort of one big idea and we're making a bunch of products that I hope will be really useful. And at some level, each product is pretty easy to explain. But the most exciting thing is sort of what they all mean together. That's what I'm going to try and talk about here today, though I will say up front that even though I think it's a really important story, it's not a particularly easy story to tell. Let me start, though. So at the core of pretty much everything is what we call the Wolfram language, which is something we're just starting to release right now. So the core of this Wolfram language has been kind of incubating in Mathematica for more than 25 years. It's kind of been proven there. But what just happened is that we got all these new ideas and technology from Wolfram Alpha, let's see, I need to but both from Wolfram Alpha and from the cloud, and they've let us make something that's really qualitatively different, and that I'm really excited about. Okay, so what's the idea? It's really to make a new kind of language, a language that's knowledge-based, a language where built right into the language is huge amounts of knowledge about computation and about the world. See, most computer languages kind of stay close to the basic operations of a machine. They give you lots of good ways to manage code you build, and maybe they have add-on libraries to do specific things. But kind of our idea with the Wolfram language is exactly the opposite. It's to make a language that has as much as possible built in, and where the language itself does as much as possible, to make sort of everything as automated as possible for the programmer. Okay, well, let's actually start it up and give it a try. So you can use the Wolfram language completely interactively using the same notebook interface mechanism that we built for Mathematica a long time ago. Okay, this is a good sign. So let's try something slightly harder. Let's say we compute something like that. Okay, we've got that's a number with lots of digits here. Wow, lots of digits. Happen pretty quickly. Kind of looks like a bunch of random digits. It might be sort of some huge number of digits in some data from some sensor or something like that. Let's see how many digits it has. Okay, so it's about 60,000 digits there. How do we analyze all of that? Well, that's something that's Wolfram language has all sorts of stuff built in to do. So, for example, we could say what's the mean of all the digits that are in there. We can ask for the numerical value of that, or we could ask, what's the skewness of the distribution of digits, and so on. Hundreds of other statistical kinds of tests. Or we could, for example, ask to make some kind of visualization of those digits. That's actually kind of odd. Okay. Or we could, let me not get derailed thinking about why it goes up like that. Okay, let's do something completely different. Let's instead go and so the Wolfram language knows about all kinds of things in the world. So, for example, one thing it knows is how to get data from Facebook. So I have here some kind volunteer let me connect to their Facebook account. My own one is kind of boring. Oh, that's a bad sign. That's a very bad sign. Okay, I think this is not going to work. Dear, oh dear. Okay. For that, I have to have some key, which I don't have. So, oh well, sad. Okay, I was going to show you a lovely Facebook network and show you how we can analyze that. Okay, well, imagine, I'll tell you what, I'll make instead of that, I'll just make some random network here. How about, let me make a random 300 node network. And the thing that this won't be as exciting as what we get from Facebook, but there's a faux Facebook network, okay? What's perhaps a little interesting there is the fact that in the Wolfram language, things are sort of automated enough that this graph that I just generated got laid out automatically in kind of an aesthetically appropriate kind of way. All right, let's try something different, see if this works. Let's try capturing a current image from a camera. Come on, work. Ah, very good, that worked. Okay, that wasn't that exciting an image because I just have the camera pointing at practically nothing there. Well, let's try doing something to that image. Okay, so let's take that image and let's partition it into little blocks of size 50. Okay, so there's that image now broken up into little blocks of size 50. We can let's make that process of doing that dynamic. So let's go and do this and go down here, and now I can pick up this camera, and there we go. And so it's kind of broken up in a weird way, but there it is. It looks kind of cool. So maybe we can let's do the following. Let's actually make a version of this. Let's kill that one off, and let's make a version of this that has things. How about let's make a version that has each little piece rotated around, so we can do the same kind of thing there, and we have so that line of code there is what it takes to kind of get that dynamic image generated that way. So maybe we can looks kind of weird here. Let's try. How about we point this at you guys, and we do something like this. We take all those pieces of image and sort them in some way. Okay, there we have something. And now let's take that, just make some picture out of it. Okay, here we go. And then let's see. I can perhaps let me make an image out of that. And oh. Let's see, I know what I want to do. It's always very nice to actually be able to use one's system kind of in real time here. Let me just stop that doing that. Okay, all right. So we've got now some image which is actually looks pretty weird. It's sort of a fragmented image of you guys. And I thought it might be fun, if this works, to actually see if we can have this connect to Twitter and actually send this out as a tweet. Let's see if that worked. No, that didn't work. Very bad. Oh well. I think something is wrong with the way that we're connected to the network here. Oh well. Okay, that's a pity. All right. So the whole point of a lot of what I'm talking about is that the Wolfram language just intrinsically knows lots of kinds of things. So, for example, it should know, if all works according to plan, there we go. So it would know, for example, when sunrise was today, and it knows from GeoIP information where it is. Or, for example, we could ask it, what's the difference in time between sunrise tomorrow and sunrise today? Okay, it's roughly a day. How about we say, well, how about we say sunrise today minus sunset today? Okay, so that's about half a day. Or we could ask it to show us something like to say what's the air temperature data for this GeoIP address. Okay, so it says that, or we could say, for example, what's the time series of air temperatures for here between yesterday and now. And now we could say something like we could ask it to just make a plot of that. And there we'll get the result. So I guess it's just getting warmer now today. So one of the things that's sort of a big feature of all of this is that given what we've done with Wolfram Alpha, we can understand lots of natural language. So one of the powerful things that lets us do is to refer to things in the real world. So for example, if I type something like this, NYC, it will know that what I'm talking about is New York City. And this will then become an entity, a New York City entity that we can do computations with. So for instance, we could just say, something like, what's the air temperature here minus the air temperature in New York City. And so then that will give us the result. So we're using kind of lots of real-world data together with some linguistics to input that kind of thing. Okay, let's do some more here. So let's say let's do something like this. Let's say, what are the neighbors of Ukraine, let's say. Okay, so there's the result, a list of entities. Maybe we could ask it to give us the lengths of those borders, and that's something it will know. And we could say something like, just take that and make a grid of values of that thing. Or for example, let's say we want to make a more elaborate visualization. Maybe we could make a word cloud out of that. So this is this little piece of code here. Let's try running it. Okay, so that little piece of code took the data I just got and made a word cloud to display that. Or let's say we could find, let's do this. Let's make a list of a bunch of, let's do something like this. Say former Soviet republics, and there it'll give us a list of former Soviet Union countries. Now, for example, let's say we want to find the flags of those countries. So again, we can do this, and we'll get the result there. And let's try, for example, given that those flags, let's take those flags and let's ask a question like, which of those flags is, by some visual nearness measure, closest to the French flag? So let's try computing that. Ooh, that's a bad sign. Okay, I think I know what happened there. Let me just try doing that and doing this again. There we go. Okay, so it figured I don't know what country's flag that is, I'm afraid, but that's the one which even I know looks a bit like the French flag, more so than any of the others here. So okay. So let's for example, let's do something else here. Let's take the first few of those. Let's do the following. Let's take let's find. Oops, that's not what I wanted to do. Let's just find. See if I could just type this myself. It'd probably be easier. Okay. So let's say I want to find the capital cities of those former Soviet republics. Bad sign. Let's see what happens here. Okay. Let me do this myself. So let's go. Like this, and then we can say, let's get a list of those entities. Okay, now let's say, let's get the entity value of capital city. Okay, so this should tell us, okay, there are a bunch of capital cities. And now let's try something else. Let's try asking it to give us the, to make a map that's based on taking the first four of those capital cities and making a disk, a 10-mile radius disk around those cities. And let's see if we know enough to do that. Okay, there we go. So I think that's pretty neat that you can just, within your language, you can just write a line of code and get something like that generated. Well, thanks. So we've been building a huge amount of knowledge into the Wolfram language. We've been sort of building this for a quarter of a century now, and there are all kinds of different domains of knowledge and computation that are built in. There are two big principles that we followed. The first is maximum automation, kind of automate as much as possible. The idea is you define what you want the language to do in a particular case, then it's up to the language to figure out how to do it. There might be hundreds of algorithms for doing different cases of some particular kind of thing, but what we want to do is sort of to make a meta-algorithm that selects the best way to do whatever you're trying to do. So that kind of all the human has to do is to define their goal, and then it's up to the system to do things in the way that's fastest, most accurate, that has the best looking results, and so on. Okay, so let me show you an example of that kind of thing. So let's say, let's go back here. Let's say that I have, I'm interested in doing machine learning. So here's a really, there's a function called classify, for example. It's just this one function that tries to use all kinds of different machine learning techniques to classify things. So in this case, we've given it a tiny training set of handwritten digits, and they're produced a classifier function for that should classify things according to that list of digits. And let me see if I go here and let me see. I guarantee I'll draw something that it can't recognize, but let's just try. Let's try drawing an 8. That was a really bad 8, but let's see what it does with it. It thinks it's a 4. Well, it's a small training set. What can I say? So one big principle of the Wolfram language is automate as much as possible. Another big thing about the Wolfram language is make everything as coherent and unified as possible. So we want to make everything in the language fit together. So even though it's a huge system, if you're doing something over here with geographic data, we want to make sure it fits perfectly with something over here that you're doing with networks, let's say. And let's see. So I've spent probably a decent fraction of the last 25 years of my life implementing the kind of design discipline that's needed to make that happen. It's been quite fascinating, been very hard work, and so on. Spending sort of a lot of time to make things obvious, to make it so it's easy for people to learn and remember and guess what's going on. But you know that having all these building blocks fit together, this is also where kind of the most powerful new algorithms come from. And we've had a great time inventing tons and tons of new algorithms that are really only possible in our language, where we have all these different areas integrated together. And there's actually a really fundamental reason that we can do this kind of integration. It's because the Wolfram language has a fundamental feature, and that feature is it's a symbolic language. So what does that mean? Well, that means that, let's go back here. So that means that if you just type an X in the Wolfram language, it doesn't give some error about X being undefined. It just says, okay, that's X. That's a symbolic thing X, and the language can deal with that. Well, of course, having things be symbolic like that is great when you're doing things like math. You know, you can compute all sorts of good math with things being symbolic like that. But as far as I'm concerned, one of the biggest discoveries that we've made over the past 25 years is that this idea of having a symbolic language is also incredibly powerful for zillions of other kinds of things too. So sort of everything in our language is symbolic. So, you know, and everything is represented in a very uniform way as a symbolic expression. So there's kind of a mathy kind of thing. And we can also have something like an entity, like let's say if I type Austin here, it will interpret that, okay, it's the city of Austin, and if I say what's the full form of that, it'll say, okay, it's an entity, it's city, Austin, Texas, US, and so on. Everything here is just a symbolic expression. Same thing with something like a piece of graphics. Let's say we have something like this. That's also just a symbolic expression. Or we could, let's say, we could make a collection of cylinders, and now again, they're just represented as symbolic expressions, which happen to be displayable as a piece of 3D graphics here. Okay, so and now, you know, everything, because this is just a symbolic expression, you can do whatever you want with it. So for example, we could perfectly well say, you know, take that and edge detect that picture, and there we'll get the result where it's applied image processing to that particular thing. So another area where having everything be symbolic is important is in interfaces. Interfaces are just another example of something that can be represented symbolically. So there's a slider, and like, for example, we can just use here's something which will now just generate a whole array of sliders. It'll work. Or we could, we can generate all kinds of weird interfaces. So let me show you. Once everything is symbolic, there's lots of things you can do. So you can let me just show you some sort of basic symbolic operations. That's just a function that successively nests some symbolic, some arbitrary symbolic function. Or you could take something like this, where you can nest a function that frames things. Or let's do something a little wild. Let's take an interface element, and let's progressively nest that interface element. That's actually pretty weird. So it's some kind of weird fractal interface. That's someplace here. Oh, I think I have to go to a higher level in the interface in order to click pieces of it. Okay, they're not a very usable interface in this particular case. But so anyway, once everything is symbolic like that, it's really easy to hook things up. So for example, let's say we've got some 3D graphic there. We can easily just say make a version of that that is manipulable. So here we have that same thing, and we have just a slider here that we can use to manipulate the computation that's going on there. Well, we can do that same kind of manipulation with anything. So like, for example, here, oops, here we can say something like generate a piece of math, and we can manipulate that perfectly well too. It's the same kind of symbolic expression idea lets us connect all these different pieces together. So here's another thing that can be represented symbolically, and that's elements of documents. So for example, here let me just generate a little sort of textual element. Let's see, we could make it fancier. Let's set it up with a manipulate here. Let's set it up with that line of code so that we have it, and we can twirl those pieces of text around if we want to. All those kinds of things. Well, this is so documents, and for example, the document I've been typing into, this is all just another symbolic expression, and we could even go and look and see what the symbolic expression is that corresponds to that thing I just typed, and so on. So it's everything that we're dealing with in documents, for example, is something that we can manipulate in the language. Well, here's another thing that's a symbolic expression, and that's code. So every piece of code in the Wolfram language is just a symbolic expression that can be picked up and manipulated just like a piece of data, passed around, and run wherever you want. Well, that's incredibly important for programming because it means you can build things in a really modular, incremental way where every piece of code that you write, however small it is, can stand on its own. But it's also important for another reason. It's a great way to interact with the cloud. It sort of treats the cloud as a giant repository of symbolic lumps of computation. And in fact, we've built this whole infrastructure for doing that I'm going to try and demo here for the first time today. So let's say we've got some simple symbolic expression. Okay, there it is. There's a little symbolic expression that says "Hello World." Now, let's see if we can deploy that to the cloud. So what we're doing here is we're just saying cloud deploy of this thing exported as a GIF, and there we'll get back this cloud object. We go there, and there it is. So that was so we just took that thing and got a symbolic cloud object with a URL that we can go to from anywhere. Well, so let's try making this not just static content, but actually a program. So for example, here we could take let's see, go back to let's go back here, and let's take something like this. This defines a symbolic piece of code that we can then go ahead and just say cloud deploy that symbolic piece of code. Okay, so now we get something here which is actually a okay. So let me explain what's going on here. This is a way. Let me type something in that will make sense to this. Let's see. I think I called it size equals 170. There we go. Okay. So what is this? This is kind of an instant API. We've created this symbolic function in the Wolfram language, and then we just said deploy that to the cloud, and we instantly create an API that we can go and fill parameters into and call from anywhere on the web. So, and every time you do this, it'll be calling back into the Wolfram cloud, doing the Wolfram language evaluation and sending back the results. Okay, so let's try, I don't know, we can try making something slightly more elaborate here. Let's see, how do I get this? I think best thing to do is that. Okay, so let's say we want to make let's instead of making a an API, let's try and make a form on the web. So now I will have specified a form function, and now I can go ahead and say this, and now that will have just created a form. We say I want size 170, angle 50 degrees, for example. See what that does. Okay. Oh, cut it off slightly, but so what that did was it ran from that form. We were just able to run this. We execute things in that form, and we're running. I see this wrapped around because it's kind of clever of it actually to figure out that it has to wrap it around when it's that size. Let's just say size 80 or something. Okay, there we go. So what's happening here is from that little piece of symbolic code in the Wolfram language, we created a form which then executed this piece of symbolic code in the Wolfram cloud that then generated a picture. Okay, let's try doing a slightly more elaborate example. Let's say we want to create a form. Let's say we have a form that we can show what's happening here. We can have a form where we fill in 2 cities, and it's going to give us a plot of a path between them. Actually, let's just go ahead and deploy that in the cloud. So there's the code that says we've got a start city and an end city, and we're going to make a geolist plot between them. Oops, I have to cancel that form, otherwise it's not going to. There we go. Okay, so now that will have produced something in the cloud, and let's try typing in, I don't know, New York City, and then let's type, I don't know, let's try Sydney there. Okay, let's submit that. And now what's going on here is this form is communicating with the Wolfram cloud, and oh, it's a little small, but here, let's make it a bit bigger. I should have told it to make a bigger picture, but there it is anyway. That's the image that it generated from that little tiny piece of code. So I think it's pretty neat. I mean, that's all it took to do that, and everything else was sort of completely automatic. Well, let me say something about how this kind of works. What we're using here is quite a stack of technology, because we have to use natural language understanding to go. I forget what cities I typed. New York City and what did I type? Sydney. Okay. So here I made a slightly simpler version. This is just a form function that says, show me the start and end cities. And what's happening here is it's requiring that it be a city. If I tried typing in something here, if I tried typing something like that, then it would complain that it isn't a city, go and try again, and so on. So it's using natural language understanding. And actually, if we go look at this form here, we'll find out that this form is now very big. Okay, we find out this is a thing we're calling a smart field, which is a field that is backed by natural language understanding, where it goes through the natural language understanding layer to actually get to something that it can run. Okay, I thought I might do one sort of modern programming example based on this kind of technology stack. Let's do something. Let's see. Let's do something kind of goofy. Let's ask for an image of a dog. It should be something that we know. And let's say that's a good result. Okay. So maybe we can have an image of a cat as well. But anyway, I picked up a couple of these, and now I'm saying cloud deploy a form that has a selector. So my goal is I'm going to have a startup that is going to make a little app that shows you what your cat or dog would see in its visual system for an image that you take a picture of, let's say. Okay? So what's happening here, now we just deployed this, so we got a form which shows us we can select between cat and dog. Okay, that's not too exciting. Let's imagine then that we go to the literature on vision systems of animals, and we find out that there's we find out that you can model the color channels for a dog with something like that, and you can model, you can model the whole sort of image that a dog sees by something like this. And now we can go ahead. Let's just pick up one of those pictures and say, show us the dog image version of that picture. Okay, there it is. Well, now we can take what we've done and let's go ahead and just make make something that we can deploy in the cloud based on this. And there we've got something that we can now go ahead here and we can deploy that. It says choose a file. Oh, I don't know where there's a file. Never mind. Let's okay. Actually, I've got a better idea. Let's so we can do that there on the web. We could also go ahead and do something else, which is we can send this over to become an app. So let's do that, and let's say I think I have to say here permissions is public. Let's redeploy that, and now what should happen if we switch? Can we switch to something which will show this this display? Yes, maybe. Oh, except it's probably at a weird angle because I can't see what it looks like. There we go. Okay, let's hit the Wolfram Cloud app, and let's see. There we go. Okay, so now we've got here. We should have. Okay, there's our. Oops, not visible. There is our cat and dog little mini app that's been deployed, and now I can say choose a file here, and it says take a photo. Okay, let's go ahead and take a photo here, and now let's say down here, let's say use that photo, and let's go ahead and say submit that. And what should happen, if everything works, is that we get an error message which says that the peak memory limit was reached because we have probably the wrong kind of account set up. Oh well, but it almost worked. And so okay, let me talk about actually the very first product that's kind of emerged from all of these things. The thing we call the Wolfram Programming Cloud should be available in a few weeks. It's all the stuff that I've been showing you, but all happening in the cloud, including the programming side of it. And there's a desktop version of it as well. But what we're seeing here, so we can just go, and everything that I've done is also available in the cloud. So I can go and I can do these computations here, and I could, for example, I can go. I hope I can go and I could make a plot here, and this is all happening just in a web browser. There's nothing, but the computation is being done in our cloud. Or I could, for example, take that, and I could, let's say, I could edit this, and I could turn this into something where I'm saying manipulate that plot, put a parameter into it, and now what I will have, I hope, is something which is a, oops, what did I just type? I did the wrong thing here. I typed the wrong thing. Okay, I have something that I can go ahead and just manipulate interactively, and all the computations there are just happening in the cloud. Well, I could also, for example, I could define a function. Let's say I define some function here, some factorial function. I can now, from within the cloud, I can go ahead and deploy that. I could say make an instant API, okay, it knows that I've defined a factorial function in this session, so take that and go ahead and publish an API based on that factorial function. And now I'll have some URL that I can go to run that particular piece of code. Okay, well, so I could also go and let me show you one other thing here. I could take, we have this whole notion of having computable documents. Let me see what's happening here. So here, let's do this. Okay, so here's a little piece of code that makes something interactive in my local document. But now what I'm doing is I'm saying, go ahead and deploy this in the cloud. So I take that thing, that piece of symbolic code, and I can now deploy it, and let's see what I get. Okay, so in the cloud, then that piece of code turned into this little interface here that I can then go and do funky things with. Okay? So what's interesting is that was a tiny little piece of code there that's mostly spent just describing what the interface should look like. I can then just deploy it to the cloud and have things happen there. So, okay, so we've got all sorts of technology here. I talked about this programming cloud. Another big thing that's coming is our data science platform. The idea there is data comes in from all sorts of sources, and then we have all these automatic ways to analyze it using sort of a giant meta-algorithm, as well as using sort of all the knowledge of the actual world that we have. Well, then you can program whatever you want in the Wolfram language, and in the end, you make reports. So on demand, or like from an API or an app, or just on a schedule or something. You can actually set up these whole, let me show you how you can set up an interactive, use our whole symbolic document mechanism to set up reports. So this is something which is a report that was set up to track my scary email inbox. And now if I ask it to generate a report from this, if it works, it should go through and use that, use what I specified there as kind of a template, and there's the actual results which were computed for that report. So, okay, let's see. So, well, there's all sorts of really interesting things that we can do with data with our whole symbolic language stack. Actually, we recently realized that we can make a very, very clean unification generalization of SQL and NoSQL databases and so on. We're implementing that in sort of 4 kind of transparent levels from in-memory to in files and databases, distributed, and so on. Another thing we've got is a very good way to represent individual pieces of data. It's a thing we're calling the Wolfram Data Framework. And basically what it is taking the kind of algorithmic ontology that we built for Wolfram Alpha and that we know works, and exposing that, and then using our natural language understanding to be able to take kind of unstructured data and automatically convert it to something that's structured and computable. And for example, our data science platform can do really good things with that. Okay, so another big thing, a rapidly increasing source of data out there in the world are connected devices, and we've been pretty deeply involved with those things. Actually, one thing I wanted to do recently was just to find out what connected devices are out there in the world. So we have this project to just curate the collection of devices out there. There are about 2,500 of these devices that we know about. We find new ones every day. We're using WDF, needless to say, to sort of organize this data about devices. And so there's sort of the quantities that all these devices measure and so on. So there are all these devices, they measure things, do things. At some point, each device typically makes web contact. And one thing that we're doing with our data science platform and everything is to create a really sort of smooth infrastructure for handling things from there on out, for sort of visualizing, analyzing, and computing everything that comes from sort of the Internet of Things. Actually, even for devices that haven't made web contact, we've got a whole framework for dealing with those, and I had a little Arduino thing up here, which I was going to show, but let me not do that because I'm going to run out of time otherwise. But let's, so one thing is connecting to a device from the Wolfram language. There's actually another thing that's coming too, which is actually being able to put the Wolfram language onto devices. And it's really nice that we've had sort of 25 years of quite tight software engineering, and this is a place where that pays back, because as soon as devices run things like Linux, we can pretty much run the Wolfram language on them. And so, for example, there's actually a preliminary version of the Wolfram language that's now bundled on the Raspberry Pi computer. So it's kind of neat to have these little $25 devices that persistently run the Wolfram language and can connect to sensors and actuators and so on. And every little computer out there that's connected can be represented as just another symbolic object in the Wolfram language. And so then it's trivial to kind of use the built-in parallel computation capabilities of the language to like pull data aggregated from lots of those machines. And going forward, you can expect to see the Wolfram language running on lots of embedded processors. There's kind of another kind of embedding that we're interested in too, and that's kind of software embedding. We want to have kind of a universal deployment system for the language. The idea is that we should be able to, given a Wolfram language program, we should be able to deploy it everywhere. So here's one example of a deployment, being able to call the Wolfram language from other languages. And we have a really easy way to do that. So for example, let's say we have, let's say we've defined some, let's get rid of that now. Let's say we've defined, lots of things to get rid of here. Let's say we've defined some API function here. So this is just a symbolic function. Now we can say, I want to embed that code in Python. So now what I can do is just say embed code Python, and what I'll get is this sort of embeddable code thing which will then call the Wolfram Cloud and be able to call that function in the Wolfram Cloud. Or alternatively, I could say, you know, embed that in Java. It's slightly more complicated. And I'll get a list of libraries and then a bunch of code that I have to put in order to be able to call that Wolfram language code from inside a Java program. So you can, and there's going to be ways to do that kind of thing from all sorts of IDEs. There's one from an Eclipse IDE where you just go in and tell it what Wolfram language code you want to include from within some other language's code, and you can also use natural language and so on to specify the code you want to generate, and this will automatically then happen and produce something in the Wolfram Cloud. Actually, there's even another concept, which is to have an embedded Wolfram engine that you can run locally as well. And essentially the same code that you just created that will run on our cloud will also run locally, but now you're running on your local machine, not in the cloud. Things get pretty interesting. You can put sort of embedded Wolfram engines inside all kinds of software to kind of immediately add knowledge-based capability and all those algorithms and natural language and things like that. Let me try to show you. I bet this isn't going to work, but I'm going to try it anyway. I'm going to try to show you an embedding of the Wolfram language in the Unity game engine. So let's see what we can do here. So now what we have, so there's a Unity system there. Let's have it running. Okay, we've got some cube that falls down. Now here we've got Wolfram language code, so we can go ahead and find that. That's kind of weird, but let's try running it anyway. Let's see if we can find that code. Okay, now let's see what happens if we say make a table of cubes. Okay, there we go. That was cool. Okay, so what happened there is we ran that piece of Wolfram language code, and it changed the configuration of the game engine there. Now let's say let's take something over here. Let's say we've got a let's create some kind of polyhedron over here. Okay, there's a nice polyhedron, and now let's say we make that into a solid that we now put into the Unity game engine over here. And now we could say, for example, thanks. Now let's say we give it a control panel here. We put an interactive control panel inside the Wolfram language for that object operating inside the Unity game engine. And now we can go ahead and let's try one more thing. Let's see. Let's go ahead and just tell it. Boom. There we go. Okay. So we just and it runs off. So okay. Talking of embedding, let me mention yet another part of our technology stack. I said the Wolfram language is supposed to describe the world, and so there's also a question of kind of describing devices and machines and so on in the world. Well, conveniently enough, there's a product that we brought out a few years ago that has to do with doing large-scale system modeling and simulation, and now that's getting integrated into the Wolfram language. So let me just show you a little bit of that. So here, let's say I put in, I've got a, actually that's not a good sign. That's not a good sign at all. Well, maybe I can't show you that. Oh, well, that's a shame. What I was going to show you is being able to take a model of a machine in this case an electric circuit, that you can just see in the Wolfram language. It's represented in a language called Modelica, and then you're able to run a simulation on that model within the Wolfram language, get the results back, control the simulation from that, and so on. Let's just see. I'll just do one more attempt here, but I think this isn't going to work. No, it's not going to work. So okay, so one of the things that we can do is take all this ability to model devices, have that run in the cloud. Yet another thing is we're taking the natural language understanding capabilities that we built for Wolfram Alpha and setting them up to be completely customizable, which is a big thing when you're like querying databases or controlling devices. It's also interesting when you're doing things like interacting with simulations. You know, you're looking at some machine out there in the field, and you're able to figure out things about it by just sort of talking to your mobile device, and then having that go to the cloud, get interpreted in the Wolfram language, do a simulation of the device, and send the results back to you. Okay. Well, so lots of possibilities. How can people actually use these things? In the next couple of weeks, I'm pleased to say there'll be sort of an open sandbox on the web for people to use the Wolfram language. We've got a growing collection of examples of Wolfram language code and its deployment and so on. That's here, and there's also about 100,000 live examples in the Wolfram language documentation that's on the web. Also, the Wolfram Programming Cloud, as I said, is coming very, very soon. It'll be completely free to start out developing things with it and to do small-scale deployments and so on. What does this mean? Well, I think it's pretty interesting, because I think we can really just change quite dramatically the economics of going from sort of algorithmic ideas to deployed products. Actually, if you come by our booth here, we'll be doing a bunch of live coding there. Maybe we'll even make some little products for people on the fly. But I think our programming cloud is sort of going to open up a surge of potential algorithmic startups, and I'll certainly be really interested to see what comes out. Another area that I think this is going to have a big effect on is programming education. I mean, I think the Wolfram language is sort of uniquely good for education, because it's kind of a language where you get to do real things incredibly easily. You get to see computation at work in an incredibly powerful way, and by the way, rather effortlessly see a bunch of sort of modern computer science ideas and immediately connect what you're doing to the real world. And the natural language aspect of this makes it really easy to get started. For example, let's see, if we just go, let's say I can say something like, draw a pink dodecahedron, and we can just interpret that with natural language and generate this piece of code here that draws a pink dodecahedron. So you can get started just by using pure natural language. So we're really interested in all the sort of educational possibilities here. Certainly there's raw material for a zillion great hackathon projects. Every summer, actually, we've for the last dozen years, we've had kind of an experiment running in a form of sort of project-based education. We've also been doing a camp for for high school students, and we're using kind of our experience to branch out into a lot of other ways to use the Wolfram language for programming education. I mean, I guess I've been involved in education for a long time. Our company's been doing things for more than 25 years in that area. Mathematica is incredibly widely used there, and Wolfram Alpha, I'm happy to say, has become sort of a universal tool, I think, for students. There's more and more coming. Let me show you just a couple of things. Here's a version just for something different. Let's see if that works. Just for something different, sort of globalization of Wolfram Alpha. There's a version of Wolfram Alpha in Chinese. It's rather non-trivial to make a natural language understanding system work in other languages, but the first one we've done is Chinese. There's also something that recently became available for Wolfram Alpha, is sort of an inverse Wolfram Alpha. This is a problem generator where it can generate sort of an infinite collection of problems, and I can do at least the simple ones by hand. We made it so you can't copy-paste the questions into Wolfram Alpha to get them done, which I think is a big shame. you know, we're going to be able to do all sorts of educational analytics and things through our cloud system from systems like that. Many possibilities. So we have our CDF computable documents that we've had for a number of years. And for example, here's a site that's been accumulating now about 10,000 demonstrations built with CDF. And with our cloud system, we can just directly run all of these things in a web browser using Cloud CDF. So they become really easy to integrate into all kinds of learning environments. Let's see, I think this is an example of something from Versal, which is a very recent case of using, let's see if we can, oh, I don't even know how to get to our piece of this. Okay, well, okay, I think it just asked me a question and I didn't get the answer. Well, anyway, it has a nice Cloud CDF in it. So at the other end of things, let's see. Well, let me mention, I think I'm getting short on time. So let me, there's lots of things going on in kind of large-scale corporate areas with the technology we've built. Lots of large-scale custom deployments of Wolfram Alpha for several years. Now with our kind of data science platform, we've got a kind of infinitely customizable way to build Wolfram Alpha-like things. And of course, everything is integrated between the cloud and desktop, and there are private clouds that will come as well. I think sort of this is just the beginning, because we've got kind of this whole Wolfram language stack, which is sort of a universal platform for creating all kinds of products. And we've got a whole sequence of products in the pipeline. And it's kind of exciting, this feeling that all the stuff I've been doing for more than a quarter of a century is actually coming together like this. Of course, it's a big challenge. Thanks. Thank you. There. It's a big challenge dealing with all these possibilities. I mean, we are just a little private company with about 700, I think, very talented people. We started spinning off companies a bit, like we have one company called TouchPress that makes iPad ebooks. We'll be doing more spinning off companies. We need more entrepreneurs, though. We might even take investors and so on. But okay, so what about the broader future? Well, I think about that a fair amount. I don't have much time to say things about that here, but let me say just a few further future kinds of things. In what we've done with computation and knowledge, we're sort of trying to take the knowledge of our civilization and put it in computable form so that we can essentially inject it everywhere. In something like Wolfram Alpha, we're essentially doing on-demand computation, where you ask for something and Wolfram Alpha tries to do it. Increasingly, we're going to have sort of preemptive computation, and we're building towards that a lot with the Wolfram language, being able to model the world and make predictions about what's going to happen, being able to tell you what you might want to do next. So, for example, even at a very practical level, whenever you use the Wolfram language, you'll see there's this little prediction bar that comes up, and you can go ahead and say, which will suggest things that it'll do a fairly fancy computation to suggest things that you might want to do next. And that's kind of a simple example of this kind of preemptive computation at work. But the real way you have to do that is to real way to make that work is your system has to have a lot of knowledge about you. And so I've been a big enthusiast of personal analytics for a long time. So for example, what's that? That is probably, okay, that's probably a record of every keystroke I've typed for the last decade as a function of time of day. And I've got all kinds of data like this. As we have more sensors and outsource sort of more of our memory to machines, our machines will be able to do better and better at telling us what we should do. And I think sort of at some level, the scenario that plays out is kind of the machines take over, not because they're forcing that to happen, but because they're providing auto-suggests to humans, and the humans are just following those auto-suggests. But okay, here's something I realized recently. I'm interested in history, and I happened to be visiting the archives of Gottfried Leibniz, who was lived about 300 years ago and had lots of rather modern ideas about computing. But in his time, he had only one very primitive kind of proto-computer. That's me taking a picture of it. So I got to kind of thinking about today we have billions of computers, but what's the extrapolation from Leibniz to us and then beyond? And I realized that one day there won't just be lots of computers, instead basically everything will just be made of computers. So biology has already a little bit figured out this idea, but one day it won't be worth making anything out of just sort of dumb materials. Instead, everything will be made out of stuff that's completely programmable and completely able to do computation. So what does that mean? Well, of course, it really blurs the distinction between hardware and software, and it means that these languages we create sort of become what everything is made of. You know, I've been very interested for a long time in thinking about the fundamental theory of physics, in fact, I've done a bunch of science that gives us, I think, a real possibility to finally get sort of a new direction for finding a way to find such a theory. In effect, sort of a way to find our physical universe in this giant space of possible universes out there in the computational universe. But well, here's a funny thing. Once everything is made of computers, even though it'll be really cool to find the fundamental theory of physics, and I still want to do it, it's not going to matter so much. Because in effect, everything that physics is just sort of the machine code for the universe. But everything we actually deal with will be a essentially software layer on top of that we can program however we want. Well, what does that mean for us humans? No doubt we'll get to deploy in some way in that sort of much more than biology programmable world where in effect you can just build any universe for yourself. I sort of imagine this moment where there's kind of just everything is reduced to a box of 1 trillion souls that are kind of running in whatever pieces of the computational universe they want. And what happens then? Well, there's lots of computation going on in this box of 1 trillion souls, but one of the things from the science that I've done, in particular from this thing I call the principle of computational equivalence, I think one is in a very kind of Copernican situation. I don't think there's anything sort of fundamentally different about that computation from what goes on sort of all over the universe, even in rather simple programs. I think I'm horribly out of time. Well, let me just I think there's more to say about this. Maybe another time. We'll get to the far future at a different time. I think the thing that's perhaps well, let me just say that I think this kind of trajectory where one gets to a situation where sort of everything is possible as a result of computation being injected everywhere. Actually, one might think that makes sort of the humans less relevant. I think it actually makes the humans more relevant because they're kind of what define the goals and purposes for that computation. Much more to say about that. But anyway, it's I happen to think that this sort of moment that we're in right now, where we're just on the edge of being able to sort of inject computation into everything, is a pretty exciting moment in history and a pretty exciting moment for what is possible in technology. I'm personally really pleased to have sort of lived at the right time of history to be involved in working on these kinds of things. And I'm pleased to have been able to tell you a bit about it here today, and I'm pleased that at least some fraction of the demos I tried to show worked. So thank you very much.